Hello, my name is Dominic Finelli, and this is my presentation for Physics 2211 Lab number 5, and I chose to do the Magnus effect. Introduction. The goal of this lab is to observe the Magnus effect on different planets using a coded model, allowing us to input the air density and gravity of other planets. This lab makes specific use of angular velocity and the Magnus effect. So firstly, what is the Magnus effect? So the Magnus effect is the main driving force in this experiment, and it essentially explains why sports balls curve when they are spinning in flight. And this experiment is going to test how that changes based on different atmospheres and different gravities. So as you can see, when a ball is kicked going in this direction, the Magnus force provides a force based on which way it's spinning. So in this case, the ball is spinning counterclockwise, so there's a force being applied in this direction, which is the Magnus force. So here's my first coded model for Venus. So Venus has a very high air density. It's 65 kilograms per meters cubed, and a relatively similar gravity to Earth at 8.87 meters per second squared. But I encountered a problem here when I first ran the code, as the ball was still being coded with Earth's air inside of it. So the weight of the ball is being calculated with Earth's air, which causes the ball to be way lighter than the air on Venus, which made it not go very far. So I fixed that by putting Venus's air into the ball and calculating that weight. And then as you can see, there's pretty much no curvature at all. It's just a straight shot, which is due to the super high air density that Venus has. So next we have the coded model for Earth, and this is what we're used to: 1.22 for the air density, 9.81 for gravity. And as you can see, it looks like a pretty normal curvature. The ball is being kicked a little bit to the right, so it curves all the way left. You can see from this top view, it's a lot more apparent. Again, here's the code. And then lastly, we have Mars. And Mars is very interesting because Mars has an extremely low air density at 0.02 and a relatively low gravity as well at 3.73. So again, I decided to do the ball with Earth's air and the ball with Mars's air. So both Earth's air. The ball is actually heavier than the atmosphere, so it doesn't spin as well. Which causes it to obviously have a lot less spin than it did with Mars's air. You would expect the spin to be more because of how low the air density is. But since Earth's air is in the ball, in this example right here, it doesn't spin as much. As you can see, the ball with Mars's air spins a ton, and that's because of how low the air density is again. So yeah, and again, here is the code. Potential problems. So firstly, angular velocity. The angular velocity that is being inputted into the code, which is right here on this line, is based on guess and check. I kind of determined that 80 meters per second in the y direction was an effective angular velocity to compare the Magnus effect on each planet, but that doesn't mean that that is a feasible angular velocity for a soccer ball in real life. And secondly, I used a simplified version of the Magnus force equation. So I used F Magnus is equal to S times the cross product of omega and V, where S is the Magnus force constant, omega is angular velocity, and V is translational velocity. And I use this because the actual formula for Magnus force is extremely complex, and it would have been very time consuming and complicated in order to implement that into this model. So I figured that using this formula would be much better. And it's still mostly accurate, just not 100% accurate. Lastly, which has a larger impact, gravity or air density? I determined air density to have a more significant impact. Gravity is still important because it determines how long the ball is in the air, so that's how long that the Magnus force is actually affecting the ball. But air density affects how much it actually curves. So as you can see here, with Venus, there's pretty much no curvature because of how high the air density is, and on Earth, there's much more because it has a lower air density. That is all I have. Thank you for your time.